Now let's turn our attention to example number 4. Suppose a rectangular water tank is being filled at a constant rate of 0.02 cubic meters per second. Now, let's say that the base of the tank has the following dimensions. It's got a width of 1 meter and a length of 2 meters. And we are interested in what is the rate of change in the height of the water. What's the speed at which that height of that water is changing at the exact moment when the height of the water is 1. So again, you can see here I've drawn out two different rectangular tanks, and we're going to go ahead and start to try to think about what's going to be happening with these tanks here. Now, I'm going to go ahead and just quickly, let me draw this backside here so it looks like I can see inside the tank. And I'm going to imagine that this tank is being filled with a liquid. So maybe there's like a big pipe or something like that over here. And this pipe is, gushing out a whole bunch of water that's kind of, falling into this particular tank, right? So maybe that's what's happening. And maybe I can imagine kind of, like if these sides were like made of glass, maybe I have some water in there that's starting to fill up. Okay, so I have my water inside the tank. Now I know a couple things here are constant, a couple things are fixed, so I'm going to write these in black. I know that the width is going to be 1 meter, right? And I know that the length here is going to be 2. I could draw actually the same things then down in the stopped picture because nothing down here is going to change. Now what's different in this scenario is that as the water keeps pouring in, the height of the water is obviously going to keep changing, right? The height would keep growing larger and larger and larger. So I could say that there is a value of h here, and I don't really know what it is. It's constantly changing. But I could also say then that there is a value of dh dt. There's a speed at which that height is increasing. And I don't know that value as well. What I do know, though, and what I could start to squeeze in here, is I know dv dt. Let me see if I can actually squeeze it in right here. I know dv dt is 0.02, right? I know that that's how quickly the water is pouring in. Now in the stopped picture, I can see that I'm told that I'm going to stop at exactly the moment when the height of the water is at 1, right? When the height of the water is locked in right here at h equals 1. Okay, so let's go ahead and start to think about step number 1 here on this question, which would be a formula that I could use that would relate all of the different variables that I have here. Really, the only variables that I'm working with are this h and this v. Can I think about this? Well, this actually isn't too tough. I know that v, that is the volume of this water, could be given by 1 times 2 times h, or really just 2h, right? I'm just doing like length times width times height. That would be the volume of that water in there. Okay, great. So this is actually a really, really simple equation then. To go to step 2 is no big deal. I just need to take the derivative of both sides with respect to the value of t. So on this side, I'm going to get dv dt. On the other side, I'm going to get 2 dh dt. So this is actually a really, really, really simple looking formula here. And now I just have to go ahead and state step number 3. I need to say I want to evaluate this derivative at exactly the moment in time when h is the number 1. Okay, so let's start filling in everything. I know dv dt is 0.02, and I have dh dt in here, but I don't know that. That's okay, because that's what I'm looking for. Great. I can solve for dh dt by simply just dividing both sides by 2. So that gets me 0.01, and the units are pretty easy. T here is being measured in seconds, and my height here is apparently being measured in meters. So the height of the water is changing at a speed of 0.01 meters per second. But that question was unbelievably simple, wasn't it? I mean, that went by super quick. There wasn't complicated formulas to work with or anything. In fact, something really surprising happens here. Did we ever even touch this value of h is equal to 1? No, I mean, that didn't even factor in when I was trying to evaluate my derivative. So this is kind of interesting. I'll put down here a little quick note. apparently dH dt is going to be equal to 0.01 no matter where we stop, right? That is, no matter at what point or what height we stop at, I'm always going to get this. And so what I can see then is that dH dt is constant. The height of the water here grows at a steady, constant rate. It doesn't change. And that's different than what we've seen in a lot of the previous problems, where in the previous problems, if we stopped at a different point in time, we would have measured a different amount. But of course here, this maybe tends to make sense in this scenario. If I'm dumping water into this tank at a constant rate, the height of the water should be going up at a constant rate, especially because I have a nice rectangular tank here. It's not like I have something strange like the walls are sloped or something like that. You could imagine the complexity that would occur if maybe I had a tank that looked like this, because then I don't need much water to fill up to this height, but I need a lot more water to fill up to this height. So in a tank like this, the height would grow very, very quickly, and then it would start to slow down. But fortunately in this scenario, I have such a simple tank that nothing like that seems to happen. However, we will take a look at one of those more interesting sorts of tanks in our final example for this section, which is example number 5. And we'll tackle that in the next video.